Alright guys, we're going to talk about horizontal and vertical asymptotes. Let's assume we have the graph of a function y equals 1 over x. So roughly, the graph of the function looks kind of like that, with a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. So vertical asymptotes you perhaps had done before, and those are the points where the limit as x goes to a, in this case a would be 0, goes to positive or negative infinity from different sides. So for example, in this case we would have the limit as x goes to 0 from the left would be negative infinity, and from the right would be positive infinity. We could have also had both going to positive infinity, both going to negative infinity, or the opposite of what we have right here. But whenever you have the limit being undefined and from either side going to positive or negative infinity, then you have a vertical asymptote. Horizontal asymptotes maybe you haven't done before, and those are going to be the line y equals b, where b is the limit as x goes to positive and negative infinity. So in that case you have a horizontal asymptote. What that is telling you is that the function is getting, as x grows, the function gets arbitrarily close to the x-axis, sorry, y equals 0. And similarly, when x gets smaller and smaller, as it becomes larger absolute value but with negative sign, then it's also getting arbitrarily close to 0. So the typical example for this type of problem will ask us to find the vertical and horizontal asymptotes of a function. So let's look at an example. I have a little bit of a summary right here, but I'm gonna talk about it in the next few examples. But this is just for rational functions, is a good rule of thumb. All right, so let's look at this function right here. Oh, one last thing, sorry. This is important. The graph of the rational function never crosses a vertical asymptote, but it may cross the horizontal asymptote. So whenever we're going to draw or analyze the graph of functions, it may very well happen that the horizontal asymptote is crossed. So just keep that in mind. All right, so let's look at asymptotes for this particular function. So if we want to look at vertical asymptotes, when is the limit of this function not going to be defined, or where is the function discontinuous? Well, that's going to happen whenever the denominator is 0. So let's do x to the 4th plus x equals 0, and let's try to solve. We can factor out an x, and we can then factor the cube, factoring the sum of cubes here, and I messed up because this is a minus. Let me erase that. And then we notice that this has no zeros in the reals, and this has x equals 0 and x equals -1. So my two possible vertical asymptotes are x equals 0 and x equals -1. So this is as much as you used to do in, say, college algebra, but notice though that in this case, if you calculate the limit as x goes to -1 of f of x, you would have the limit as x goes to -1 of the function x plus 1 over x times x plus 1 x squared minus x plus 1. Notice what I did here. I put in the denominator this factored expression for x to the fourth plus x. Why do I do that? Well, because that lets us know or see clearly that in the limit, this function is going to be going to 1 over x times x squared minus x plus 1, which happens to be negative 1, and here we have 1 plus 1 plus 1, so 3. So the limit here is negative a third. Notice that this is not infinite, so in that case, we only have one vertical asymptote. Well, I should confirm also that the limit as x goes to 0 of f of x does not exist, but you can see that because the term, this x will give us a 0 in the denominator regardless of this cancellation. So the limit here will not exist, and that tells us that this right here is a vertical asymptote. This one is just a removable discontinuity. So this one is not going to be a vertical asymptote. So that's one thing you have to be careful. So we have one vertical asymptote, and then horizontal asymptote. We calculate the limit as x goes to positive and negative infinity. We look at both. But in this case, both of them actually match. Notice that the degree of the top is less than the degree of the bottom. So if you wanted to calculate this limit, you will get 0. The way to calculate it is the following. If you multiply and divide the f of x, so let's write, oops, not square but to the fourth, sorry. So grab this expression and multiply it and divide it by the same term, 1 over x to the fourth. I just look at the highest power of x and I multiply and divide by it, or by the reciprocal of it. And what I achieve by doing this is I achieve an expression, or I obtain an expression of the following form. I distribute this term here and I get 1 over x cubed plus 1 over x to the fourth divided by 1 plus 1 over x cubed. This term right here, as x goes to positive or negative infinity, is going to be 0, this one as well, and this one as well. So you're left with 0 over 1, regardless of whether you're going to positive or negative infinity. It's 0 over 1, which is just 0. So you have that you have a vertical asymptote at x equals 0 and a horizontal asymptote at y equals 0. And that those are your asymptotes for this function. The reason why I didn't consider x equals negative 1, even though it made the denominator equal to 0, is the fact that the limit is not undefined. In fact, it's well defined and a real number. So I don't have any problem with that. That's a removable discontinuity. It's not a vertical asymptote. I believe I have a picture. Yeah, here we go. I have a little picture of this. You have x equals 0 and y equals 0 are your asymptotes. So that's that for this video, and I will continue with slant asymptotes, as you can see, in the next video. Thanks for watching.